Welcome back. I'm Mohammed Kadam Karai from Orange Research. Having examined the single MIMO link in part 1, we now step up one level and ask how those link level gains translate into the behavior of a whole network. Many base stations, many users, interference, traffic, and all the complications real life so generously provides. This is, again, joint work with my colleague Bartłomiej Błaszczyszyk from INRIA ENS. The formulas will still be there, I'm afraid, but the reward this time is that we'll be able to compare them directly with field measurements from real 4G and 5G networks. Here is our plan. We begin with a short introduction that situates Part 2 with respect to Part 1, and states what we are after. We then lay out the network and traffic model, the geometric and stochastic framework in which everything will live. We validate the model against operational data from deployed 4G and 5G systems. A reassuring exercise, and occasionally a humbling one. With the model trusted, we turn to the main question: how does throughput behave in large-scale MIMO networks, under both CSIR and CSITR, and under the two dominant scheduling policies? We close with a synthesis of findings, and some perspectives on where the work might go next. Let us begin with the introduction. In this opening section, we take a step back before diving into the machinery. The goal is simply to set the stage, to recall where Part 1 left us, to explain why a link-level analysis, however rigorous, cannot be the final word on network performance, and to state clearly the engineering question that will drive everything that follows. Part 1 established the fundamental limits of MIMO communications at the physical layer, quantifying ergodic capacity in bits per symbol for a single isolated link, under various assumptions on channel knowledge, and at a fixed signal-to-noise ratio. That is a necessary first step, but it is not, by itself, an evaluation of a cellular network. In a real system, the signal quality experienced by a user depends on their random location, on distance-based path loss, on log-normal shadowing, on the interference generated by neighboring cells, and on how radio resources are dynamically shared among users who arrive, download, and depart. Fixed SINR analysis leaves all of that unaccounted for. The engineering question we want to answer then is the following: what is the true value of the MIMO gains we computed in Part 1, additional antennas, transmitter channel knowledge, once traffic and interference enter the picture? The objective of Part 2 is to bridge the gap between information theory and network engineering. The tool for doing so is a physics-based analytical framework with two ingredients: stochastic geometry, to capture spatial interference from randomly located base stations, and queuing theory, to capture traffic dynamics, user arrivals, file transfers, departures. Equipped with this framework, we will map the physical layer capacities from Part 1, the CSIR and CSITR capacity functions, onto network-level key performance indicators. The primary indicator will be the mean user throughput as a function of the offered traffic, supplemented by the cell load, the average number of users, and the critical traffic demand. We now turn to the network and traffic model. This is where the framework is built. We will describe the spatial geometry of base stations, the propagation environment, and the resulting signal-to-interference plus noise ratio. We will then layer on top of this a traffic model that accounts for users arriving, downloading, and departing. And we will finish with the scheduling policies that determine how each cell shares its bandwidth. By the end of the section, we will have a single closed-form description of a mean cell, ready to be confronted with data. We start with the geometry. Base station locations are modeled as a stationary and ergodic point process, a standard tool from stochastic geometry that lets us reason about a typical base station rather than any specific one. Propagation loss has the usual two ingredients: a deterministic power law decay with distance, and a random log-normal shadowing component that captures the large-scale fluctuations due to buildings, terrain, and so on. Each user associates with the base station that delivers the strongest received power, possibly adjusted by a bias term, which is useful for handing off users between layers of the network. The central quantity is the signal-to-interference plus noise ratio, or SINR, experienced by a user at a given location. In words, it is the useful signal from the serving base station, divided by the sum of thermal noise and the interference contributed by all other base stations. A crucial point appears here. Each interfering base station contributes only in proportion to its cell load, the fraction of time it is actually transmitting. An idle base station does not interfere, which means interference, and therefore SINR depends on how busy the neighbors are. From SINR to bitrate, information theory does the heavy lifting for us. Without it, we would have to track detailed codebooks, beamforming vectors, and receiver structures, and the mapping from SINR to achievable rate would be genuinely involved. Information theory collapses all of that into a single ergodic capacity function of the SINR. The peak bit rate at a location is then simply the bandwidth, times an efficiency factor accounting for practical protocol overheads, times this capacity function. And this is where part 1 meets part 2. The capacity function is either the CSIR expression or the CSITR expression we studied previously. On top of this physical layer, we place a traffic model, a spatial multi-class queue. Users arrive according to a Poisson process, request files of random size, and leave once served. The total offered traffic to a cell is a spatial integral of demand over its coverage area. Finally, scheduling. How does the base station share its bandwidth among the active users? We consider two policies. Round robin, the 5G baseline, gives each user an equal share of time, which is fair and simple. Opportunistic scheduling, the 4G baseline, instead prioritizes users whose channels are momentarily favorable, at the price of some fairness, but with a scheduling gain that grows with the number of users in the cell. Assuming round-robin scheduling, we have first a stability condition, and then three quantities describing the stationary regime. The cell is stable only if the offered traffic stays strictly below a critical traffic demand, the maximum traffic the cell can sustain before the queue runs away, and this critical demand takes the form of a harmonic average of the peak bit rate over the cell area. Once stability holds, the typical cell is described by three further metrics. The cell load is the ratio of offered traffic to critical traffic, a dimensionless number between 0 and 1 that measures how close to saturation the cell is. The average number of users follows the classical queuing theoretic formula. It diverges as the load approaches 1, which is exactly the signature of an overloaded queue. And the user throughput admits two equivalent expressions. On the one hand, the offered traffic per active user. On the other, the slack between critical demand and offered demand. The two forms coincide, and each sheds light on the quantity from a different angle. A word on the coupling between cells. Because interference from a neighbor depends on how busy that neighbor is, each cell's load is a function of its neighbor's loads, which are themselves functions of its own. To break this circular dependency, we adopt a mean field approximation. The surrounding loads are replaced by their spatial average, and the analysis reduces to that of a single mean cell. One last word before we move on. We have stated the proposition for round-robin scheduling, because that is where the formulas take their simplest form. But the same approach, the harmonic mean characterization of critical traffic, the mean field treatment of intercell coupling, the stationary regime KPIs, extends to opportunistic scheduling as well. The details are developed in our 2019 paper in IEEE Transactions on Wireless Communications, and the complete treatment, tying the link level and network level analyses into a single framework, appears in our upcoming book, Information Theory for Discrete and General Alphabets, with applications to wireless communications and networks. Everything we present in the rest of the talk rests on that foundation. Suppose we rescale the network density by some factor. Geometrically, the cell structure scales homothetically. Same shape, different size, and, more importantly, several quality of service metrics turn out to be perfectly invariant under this rescaling. The cell load, the critical traffic, the average number of users, and the average user throughput all remain unchanged. This is a reassuring property. It says that what matters is not the absolute density of base stations, but the relation between density and propagation parameters. The practical consequence is stated as a homogeneity condition. Consider a cellular network composed of several distinct zones: dense urban, suburban, rural. If the ratio of distance loss parameters to the square root of base station density is held constant across these zones, then the network delivers a uniform quality of service response across all of them. Equivalently, any zone can be analyzed formally as a rescaled version of any other, a useful guiding principle when deploying and dimensioning heterogeneous networks. A brief word on sources before we move on. The full derivation of these scaling laws and of the homogeneous quality of service condition is given in our upcoming book. And importantly, the approach is being confronted with real field measurements from operational cellular networks in our earlier 2015 paper, which gives us some confidence that the invariance we have just described is not merely a mathematical curiosity, but a property that the real world appears to respect. We now confront the model with operational data. Up to this point, everything we have said has been theoretical, a chain of assumptions, definitions, and propositions, each one reasonable in isolation. The question that naturally arises is whether the resulting framework actually describes deployed networks, or whether it merely describes a mathematically convenient idealization of them. In this section we put it to the test. We take the predictions of the model, place them side by side with measurements collected from operational 4G and 5G cells, and see how well the two agree. Before we validate the model, a brief look at the parameters. The table on this slide summarizes the operational settings for 4G and 5G that we'll use throughout. A few highlights worth noting. 5G uses a much wider bandwidth than 4G, which is the first and most direct reason 5G throughputs will be higher. 5G also uses time division duplexing, which sacrifices a fraction of time for uplink transmissions, a detail that enters the formulas as a proportion of time factor. The baseline MIMO configurations are typical of actual deployments: a modest array in 4G, a massive array in 5G. And finally, 4G uses opportunistic scheduling, while 5G uses round-robin, which reflects how these standards were actually designed. Two further parameters deserve a word. The efficiency factor, set to 0.35 for both technologies, accounts for the practical overheads that reduce realized throughput below the Shannon limit: pilot symbols, control signaling, coding margin, MIMO correlation, and so on. The path loss parameter, finally, is related to propagation in each frequency band. The higher carrier frequency of 5G does lead to somewhat more attenuation per unit distance, as one would expect, though the difference is modest. Now, the moment of truth: does the model match reality? This figure compares our theoretical predictions, shown as red lines, against field measurements from a deployed 4G network, shown as blue dots. 3 panels, 3 quantities: cell load versus traffic, mean number of users versus traffic, and mean throughput versus traffic. The agreement is strong. The red curves pass cleanly through the clouds of measured points, with one visible exception, which we will address in a moment: a plateau in the throughput curve at low traffic. The same 3-panel comparison, now for 5G. Again, the theoretical predictions track the measurements well across the traffic range. The same low traffic throughput plateau is visible here too, and once more a small discrepancy in the load panel, which we will also discuss next. So what about those discrepancies? 3 things are going on, and, reassuringly, none of them reflects a failure of the physical layer model. First, the low traffic throughput plateau, in both 4G and 5G, is not primarily a physical layer effect. It is driven by TCP slow start. Short flows never reach the available bandwidth, and by application-level throttling, video streaming services capping their own bit rates being the canonical example. This is above the layer our model describes, and is expected. Second, in 4G, the model slightly overestimates throughput. The reason is simple. The model assumes a uniform baseline configuration with 4 antennas at the user side, whereas the field features a mix, with 2 antennas at the user side being common in practice. Fewer receive antennas than assumed means lower capacity than predicted. Third, in 5G, a bias in the load measurement itself. The theoretical load is strictly temporal, the fraction of time the base station is transmitting useful data. The operational counters, however, track physical resource blocks, which include control signaling overhead. This inflates the baseline measured load relative to the theoretical quantity. The takeaway is a clean one. Once protocol overheads are contextualized, the macroscopic model reliably predicts the fundamental scaling laws across both technologies. We now arrive at the heart of Part 2, throughput trends in large-scale MIMO networks. With the model built in the previous section and validated against field data in this one, we are finally in a position to use it for what it was designed to do, to ask how network-level throughput responds as we vary the parameters that matter most. the number of transmit and receive antennas, the presence or absence of channel knowledge at the transmitter, and the choice of scheduling policy. We will work through 4 figures covering the 2 technologies, 4G and 5G, under each of the 2 channel knowledge assumptions, CSIR and CSITR. Each figure is followed by a short commentary extracting the engineering lesson. The goal, by the end of the section, is a clear picture of where the gains come from, and just as importantly, where they do not. With the model validated, we turn to the main question. How does network-level throughput behave under large-scale MIMO? We begin with 5G under CSIR, receiver-side channel knowledge only, equal power allocation at the transmitter, and round-robin scheduling. This figure shows mean user throughput against offered traffic for different numbers of transmit antennas, with the number of receive antennas held fixed. On this slide, 1 receive antenna on the left, 2 on the right. Each curve shows the same qualitative shape, a throughput that decreases almost linearly with offered traffic, and then collapses sharply at a critical traffic demand, beyond which the cell is unstable. Continuing. 4 receive antennas on the left, 8 on the right. The same collapse pattern appears, but the critical traffic demand shifts as the antenna counts change. The next slide will interpret the trends. 3 observations on these 5G CSIR results. First, throughput collapses exactly at the critical traffic demand, an absolute stability limit. Second, and more interestingly, doubling the transmit array from 32 to 64, while the receiver stays at 4, brings a negligible improvement in critical traffic. The top 2 curves sit essentially on top of each other. Third, and this is the structural reason, network capacity under CSIR is strictly bounded by the smaller of the 2 antenna counts. This is the same bottleneck we identified at the link level in Part 1, now faithfully reappearing at the network level. Massive transmit arrays require equally capable user equipment to unlock their spatial multiplexing gains. The same study, now for 4G. The physical layer assumptions are unchanged, still CSIR, still receiver-side channel knowledge only, still equal power allocation at the transmitter, but the scheduling policy is different. 4G networks use opportunistic scheduling rather than round-robin, and the shape of the curves reflects that change. The throughput no longer decreases linearly with offered traffic, but instead follows a convex decay toward a horizontal asymptote. The bandwidth, of course, is also narrower than in 5G, 20 MHz instead of 90, so we should expect the absolute throughput values to sit at a lower level across the board. The structure of the figure is the same as before. Mean user throughput against offered traffic, with several curves corresponding to different numbers of transmit antennas. On this slide, 1 receive antenna on the left, 2 on the right. Continuing. 4 receive antennas on the left, 8 on the right. The curves have the same qualitative shape as on the previous slide. A convex decay toward a horizontal asymptote at 0 throughput, and the contrast with the linear 5G curves remains visible. What changes across the 4 panels of this figure is the location of the knee of each curve, the traffic level at which throughput starts to fall off sharply, and the rate of descent beyond it. Both depend on the number of transmit and receive antennas, and we will interpret those dependencies on the next slide. 4 observations on the 4G CSIR results. First, the fat-tailed, highly convex shape comes directly from opportunistic scheduling. The scheduler leverages larger user pools to extract a larger scheduling gain. More users means more chances to find one with a favorable channel at any given moment. Second, a word of caution. The throughput gains shown here assume fading variance that is always available. For very large transmit arrays, however, fading tends to average out, a phenomenon known as channel hardening, and the scheduling gain shrinks. So the curves should be read as a mathematically optimistic upper bound in that regime. Third, the spatial bottleneck is visible again, and most clearly in the comparison between 32 and 64 transmit antennas. Across all 4 panels of the figure, whether the receiver has 1, 2, 4 or 8 antennas, doubling the transmit array from 32 to 64 brings essentially no gain. The 2 curves sit almost on top of each other. Past a certain point, additional transmit antennas stop contributing, and the smaller of the 2 antenna counts dominates. Fourth, and straightforward, 4G curves reach lower throughputs than 5G ones, simply because the bandwidth is smaller, a direct scaling with the available spectrum. We now switch on transmitter channel knowledge, CSITR, and water filling power allocation. Same figure layout as before, 5G, with round-robin scheduling. 1 receive antenna on the left, 2 on the right. The visual difference compared with CSIR is already striking. The critical traffic is pushed much further to the right, especially for larger transmit arrays. Continuing. 4 receive antennas on the left, 8 on the right. The pattern established on the previous slide holds and intensifies here. Transmit arrays that barely helped under CSIR now make a dramatic difference. Looking across the panels, the curves for different transmit antenna counts no longer collapse onto each other as they did under CSIR. Each additional transmit antenna pushes the critical traffic demand further out, and the spread between the T=4 and T=64 curves is now substantial. The shape of each curve is the familiar near-linear decay of round-robin scheduling, but the range of traffic over which the cell remains stable has expanded considerably. The next slide will quantify the gain and explain the mechanism behind it. 3 observations, of which the first is genuinely remarkable. First, with CSITR, network throughput continues to grow substantially as transmit antennas are added, even when the receiver has only a single antenna, something CSIR flatly cannot do. The spatial bottleneck is no longer limiting. Second, a concrete number to anchor this. A 32x4 array under CSIR, saturated at a critical traffic around 60 megabits per second. With CSITR, the same array sustains a critical demand approximately 4 times that. Third, the mechanism. CSIT allows the base station to concentrate power during favorable fading states, and back off when the channel is poor. A temporal selection gain. Excess transmit antennas, which under CSIR were essentially wasted, are now converted into what is effectively a stability multiplier at the network level. Finally, the most synergetic combination, 4G, with CSITR, and with opportunistic scheduling. 2 mechanisms are at work here simultaneously. The temporal water filling, enabled by transmitter channel knowledge, which we saw on the previous pair of slides, and the multi-user diversity exploited by opportunistic scheduling, which we saw in the 4G CSIR figures. Each one individually already improved performance substantially. The question this figure answers is what happens when both are active at once. The figure structure is the same as before. Mean user throughput against offered traffic, with curves for different numbers of transmit antennas. And on this slide we have 1 receive antenna on the left, 2 on the right. Continuing. 4 receive antennas on the left, 8 on the right. The curves here are particularly striking, strongly convex, with critical traffic demands far beyond what we saw in any previous figure. The spread between the curves for different transmit antenna counts is the widest of the 4 figures we have presented, which is the visual signature of the 2 gain mechanisms reinforcing each other. Looking across the 4 panels of this figure, one sees that the benefit of adding receive antennas is also preserved. The knee of each curve moves further to the right as the receiver grows, so that the configuration with 32 transmit and 8 receive antennas, shown in the bottom right panel, operates at traffic levels that the CSIR figures simply could not reach. The figures speak loudly enough on their own, but 3 observations are worth making explicit. First, the spatial bottleneck is entirely broken. Even with only 2 receive antennas, the 32 transmit configuration now pushes the critical traffic beyond 250 megabits per second, compared to just 40 megabits per second under CSIR. A more than 6-fold expansion of the stability region, on the same hardware, from channel knowledge alone. Second, this is what happens when 2 diversity mechanisms compound: temporal water filling, provided by CSITR, and multi-user diversity, provided by opportunistic scheduling. The 2 stack to produce exceptionally robust and highly convex throughput curves. Nevertheless, this dual optimization is something of an idealization, because massive arrays harden the channel, reducing the inter-user variance that opportunistic schedulers actually rely on. So the figures shown are best read as an upper envelope of what is achievable in this regime. Third, and perhaps the most conceptually satisfying point, CSIT restores a form of symmetry between the transmit and receive sides. Under CSIR, adding transmit antennas beyond the number of receive antennas brought only marginal gains. With CSIT, Those extra transmit antennas are no longer wasted. Each one translates directly into a temporal selection gain, pushing the fundamental capacity boundary of the cell outward. Receive antennas still help, and they help a lot, but transmit antennas have, in a sense, been given back their usefulness. And with that, the technical arc of Part 2 is complete. We have built the model, confronted it with operational data, and used it to chart how MIMO gains translate, or fail to translate, into network-level throughput across the 4 regimes defined by scheduling and channel knowledge. It remains to step back, draw the threads together, and consider where the work might go from here. Let me draw the threads together. 4 main findings. First, the CSIR spatial bottleneck is real and unforgiving. Without transmitter channel knowledge, network capacity is constrained by the smaller of the transmit and receive antenna counts. Scaling the network, therefore, requires upgrading user-side antennas, not just base station arrays. Second, the transformative power of CSIT. Water filling converts spatial degrees of freedom into temporal selection gains, dramatically extending stability boundaries even for limited user equipment. Third, scheduling matters, and it interacts with channel-side information. Round-robin produces linear degradation curves. Opportunistic scheduling, by contrast, yields highly convex and resilient performance curves, and compounds particularly well with CSITR. Fourth, the model works. Theoretical predictions accurately match field measurements from deployed 4G and 5G networks, once protocol-level effects, TCP slow start, application throttling, resource block accounting, are properly contextualized. Looking ahead, 4 directions stand out as natural next steps. First, further validation. We would like field data from operational networks using more aggressive MIMO configurations, genuine massive MIMO, to quantify the real-world spatial multiplexing gains against our curves. Second, multi-user MIMO. The present framework treats each cell as a collection of point-to-point links. Extending it to model genuine broadcast channels, where the base station serves several users spatially at the same time, would unlock another dimension of gain. Third, data-driven modeling. The mean cell physics approach is powerful for understanding, but it averages away local detail. Supplementing it with machine learning, to predict topographical anomalies, unusual interference patterns, and deployment-specific effects, is a natural complement rather than a replacement. Fourth, imperfect channel state information. All of our CSITR results assume perfect channel knowledge at the transmitter. In practice, channel estimation has latency, signaling cost, and estimation error. Modeling these explicitly is the natural next step toward realism. As in Part 1, the network-level framework and numerical evaluations presented today are drawn from our own book, Information Theory for Discrete and General Alphabets, with applications to wireless communications and networks. The book places the link-level and network-level analyses in a single coherent treatment. And with that, we reach the end of this 2-part journey, from the log determinant of a random matrix, all the way to the critical traffic demand of a deployed 4G or 5G cell. I hope the connection between those 2 worlds now feels less like a leap and more like a short, well-paved road, with perhaps 1 or 2 long formulas serving as decorative milestones along the way. Thank you for your attention.